Hey class, hope you're doing well. Happy Friday. We're going to close these lectures with one more PowerPoint or the continuation of the PowerPoint, so if you want to take that out. Also, I know yesterday some of you didn't have the prep book. We're going to do it again today. Maybe um, I've, maybe I will, I haven't done it yet, but I'll photocopy some in case some of you do not have your prep books. But sorry I couldn't let you know earlier, sorry I couldn't be there. If you have some time after, maybe I can show you some pictures of the baby. And so once you do this PowerPoint, what I'll have you do is I'll have you do chapter 7 and 8 of the prep book, which I'll also photocopy if you need it, and also take the quizzes. Hopefully you guys don't cheat and try the quizzes to see how you do. Chapter 7 is about energy, so we're talking about energy right now, just see how you do. And the next one's about pollution. It's not one we've talked about yet, but the next chapters we're going to talk about is pollution. So where we left off on is coal. Remember we talked about the different types of coal. It goes from order of most helpful, or from least helpful to the most helpful, or the least energy to the most energy. So some key terms you need to know: peat, not a coal; lignite, which is brown coal; bituminous coal, which is soft; and then anthracite, which is hard. Obviously, coal being a fossil fuel, we have to dig or we have to go into the earth to get coal. The most common form in which we get coal is called strip mining. Here's a picture of a type of strip mining, or an example. So see how the hills are supposed to be nice and green and pretty, and when you strip mine, it looks ugly, like this one here in the front. Surface mining, it's a surface mining process in which the overlying or overlaying layer of soil and rock, they strip off that top part, and then there's this coal sitting right at the bottom. So that's called strip mining. What's the problem with strip mining? Well, if you strip and take away the top layer of the nice and pretty hill, you could drain. You get acid mine drainage, which is when if you strip the top part and it rains, then all that nasty coal stuff runs off. Land subsidence. So we're talking about sinkholes. So if you strip it long enough, like maybe the surrounding layers of land, you might sink. And also coal fires, they're highly flammable, so a little bit of fire, a brush fire, can set off a flame, essentially. The future of coal, they want to do something called scrubbing, which is a way that they can remove the sulfur dioxide and make it less polluting. Sulfur dioxide, if you remember, causes acid rain, so if they literally tried some sort of scrubbing method on coal, then maybe when you burn it, we won't get so much pollution up in the air. Another way they're trying to minimize the impact is called allowance training. So what happens is that each company, I don't know who's in charge, but they go over to each company and they say, you're only allowed to burn this much coal. So let's just say, I don't know what the units are, let's just say you get 50 units of burning, you get 50 units of burning, you get 50 units of burning. That's all that you can do. Allowance trading means, like, say if I'm a company and I barely burn coal and I got 50, maybe I could sell or trade my 50 to another company, so a company can have 100 and I have 0. Or maybe I give them 25 so they have 75 and I have 25. And we could trade credits. Technically, it reduces pollution, but obviously people abuse it. And so utility companies, they get these allowances that you can trade, so you still stay under some sort of cap. And we'll talk about that when I come back. After coal, the last part of fossil fuels is called oil, shale, and tar sands. And actually, this is what we're going to talk about with over Skype with a sister school in Canada. But these are the last type of fossil fuels, and maybe some of you aren't familiar with or seen oil, shale, or tar sands. Maybe some of you may have heard of the La Brea tar pits. Shale is a fine-grained sedimentary rock, and it's a syn fuel. So synthetic, it's not natural. It's a syn fuel. Tar sands, they're sedimentary rocks also, but impregnated or buried within the rock, there's some tar oil or some asphalt. I think some of you know what asphalt is, or bitumen. The great thing about oil, shale, and tar sands, there's actually a lot. Remember, oil is supposed to expire in about 50 years, so there's actually a lot of oil and tar, and there's large potential supplies that we get. Problem is, as you know, to get to it, it costs a lot of money. We actually don't get as much energy from oil shale than we get from coal or oil or natural gas. It takes so much water to get it. We have to do surface mining. Remember we talked about water pollution, air pollution, blah, blah, blah. It's all terrible. Okay? So that closes the door on fossil fuel energy sources. And as environmental scientists, what you need to be concerned about, or what you should care about, is what are the alternative energy sources? Alternative energy is any renewable or non-renewable energy source instead of fossil fuels. Anything that's not fossil fuels is called alternative energy. The renewable energy sources that are alternative, we're talking about solar power, water power, or hydropower, wind. Some of you may not have heard of, you may have heard of these three, but you may not have heard of biomass. And some of you may not know, but there are some alternative energy sources that are non-renewable. So nuclear power and geothermal power. They're dependent on fuels that are used up much faster than is replenished by natural processes. And we're going to talk about all of these energy sources in this PowerPoint. So nuclear energy, I want to show you a quick video. How does it work? Well, nuclear energy is basically, or the term nuclear comes from the word nucleus. All of you have taken, or should have taken, some sort of chemistry or biology where you learned about the parts of a cell, but the nucleus is the center part of the cell, and it's very dense. So to get energy, you can either do fission or fusion. I think fusion is a word that you guys know, much better than fission. Fusion means I take two nuclei and I force them together and it creates a lot of energy to put these two nucleuses or nuclei together. Fission is the opposite. Fission says I'll take a nuclei and I'm going to strike it and it splits up into many other smaller nuclei, and that also releases a lot of energy. Nuclear energy specifically is nuclear fission. So some of you may say, like, why do we have to learn fusion? There is some energy, but nuclear reactors or nuclear power plants that you know of use fission, which means I take a nucleus and I split it apart. And this part's hidden. It's hidden by the brown border, but what they use specifically is uranium for a nuclear power plant. So what I want to do is I want to show you a quick 1-minute video and maybe highlight how a nuclear reactor works. I got this from YouTube, so watch this video real quick. It takes about a minute and I'll explain it.
Produces heat. A nuclear reactor produces heat through nuclear fission, in which atomic nuclei break apart, releasing large amounts of energy. Core of the reactor, a self-sustaining nuclear chain reaction takes place.
So this is whenever everybody talks about the core or the nuclear core of a nuclear power plant or a core meltdown, this picture right here is a picture of the core.
Control rods are raised or lowered to absorb neutrons and control the reaction and the amount of heat produced. The most common type of nuclear reactor is the pressurized water reactor. It's known as a double-loop system because it uses two circuits of water. The first circuit, or primary loop, pumps water heated by the reactor core through coils in a heat exchanger. The water remains liquid even at 300 degrees Celsius because it is pressurized to a high pressure of 150 atmospheres. A secondary loop, water, converted to steam in the heat exchanger, is fed under pressure to turn turbine generators.
So let me help explain this for you if you guys are confused. So in the goal of any energy source is to spin a turbine or to spin some sort of, for lack of a better word, to spin some kind of turbine. So when you burn gas, or when you're driving in a car or a bus, you burn gas so you could spin the turbine, the engine in your car. Or in hydropower, when you have those dams, your goal is to have water pass through and spin a turbine. Or wind power, you're trying to spin a propeller to spin a turbine. Your goal in any type of energy is to spin a turbine. This is how nuclear energy works. I'm starting here with these rods. And remember I told you in fission, you take a nucleus and you split it up. So these rods are rods of uranium. And we're going to somehow inside this really, really tiny core is essentially take these rods of uranium and make them split apart. That splitting apart action is super, super explosive and makes and creates a ton of heat. So what I have is this water, and if I heat it up, I get super hot water, which is in red, and it creates a lot of steam. And all the steam, because it's so hot, that steam spins the turbine, which powers a generator, which, not necessarily a light bulb, but can power a city or something. Okay? Here's where it goes, not wrong, but where the problem lies. once it spins the turbine, this water is now going to cool again, and it actually is now not usable. Okay, because we used uranium in it, and it's not very nice, and we don't want to use it. So that's where we get that radioactive waste, or maybe you've seen those barrels with that yellow sign with the forget it. You know what I mean? It's that radioactive sign. Um, Something that we can cool, we can repump it back into here and start this loop all over again. So here's two loops. Loop number one, I have a coolant that gets heated up by the rods, and it creates some steam and spins a turbine. It later then cools down and gets pumped in, and this is the loop number one. And this is loop number two. So hopefully you guys understand a nuclear reactor. Again, we could talk about it later when I get back to school. But I thought it was pretty cool. I never knew how a nuclear power plant worked until I taught this class, or took this class. So back to the PowerPoint. This is essentially in bullet point form everything we saw in the animation. So when we do fission, energy is released. You need a core, which I showed you, the control rods, a coolant, and a reactor vessel. Burner reactors are a nuclear reactor that actually consumes more material than it produces. So essentially, it consumes more energy than it makes. And then a meltdown, some of you may not know, but the reason why we don't use more nuclear power, as great as it sounds, is one, it creates a lot of radioactive waste, and two, it can actually melt down, which has happened many times before, where it gets too hot inside the core, and it forms a molten mass that actually goes outside of the reactor and contaminates the outside environment. So again, I told you, here's a picture of everything of that animation that I just showed you. So radiation, it occurs when a radioisotope, it radioactively decays spontaneously and then changes into another isotope. So radiation is something that we don't want. You can get alpha rays, beta rays, or gamma rays from this type of radiation. We'll skip breeder reactor. Some of you may be wondering, where are these power plants located? The largest one in the United States is actually in Phoenix, a little bit outside of Phoenix, called Tonopah, Arizona. And it actually powers or gives some power to Southern California and obviously parts of Arizona. It's the largest power producer of its kind in the United States. Just its 3 units generate nearly 4,000 megawatts of electricity. So if you're the type of company that needs energy or wants to create energy, again, this Palo Verde nuclear generating station generates a ton of energy. It's great, and it's semi-clean. It burns clean. You don't put any air pollution or put any pollution up into the air. It's the only nuclear plant in the United States that doesn't sit on a large body of water. I don't know if you guys can guess why most nuclear power plants sit on a large body of water. Yeah, because of those 2 loops that we're talking about. It needs it to cool. And instead it uses different municipalities to meet its cooling water needs. So it imports a lot of water, uses a lot of water to cool down its nuclear core. So the cycle of how to make nuclear energy, the only thing really, you have to mine the uranium, those little rods, or maybe some of you have seen The Simpsons where I have that nice green glowing rod. I know it's another Simpsons reference that we use for fission. Then the reprocessing of spent nuclear fuel, the decommissioning of power plants, and then disposing of radioactive waste. So this is the cycle of nuclear power. Each part of the cycle has a different environmental problem. Radioisotopes, we talked about it, isotopes that go under spontaneous radioactive decay. And this is bad for 2 reasons. One, it emits radiation, so these alpha, beta, and gamma rays can affect the environment. And 2, if it gets into, we heard about bioaccumulation before, so if something gets radiation and something eats that and we eat that, it can affect the whole ecosystem. Last thing I want to talk to you about is some power plant accidents, the 3 main ones that have happened. One actually happened in the United States called 3 Mile Island. You need to know this one for the AP exam. It happened in Pennsylvania. Nuclear meltdown, and then actually the surrounding area underwent a whole bunch of radiation. A lot of people that were in the area had birth defects and such. And the worst accident in history is Chernobyl. This is, I believe, in Russia and Northern Europe. It's the worst accident ever. Same thing in nuclear meltdown. It was theorized in the next 20 to 30 years there'll be an increase in cancer because of that. So that's the only time I have for the PowerPoint. I just wanted to show you a quick picture of the baby. There it is, or he is, my wife. So I'll see you guys. Have a good weekend. Enjoy. Get to work on your prep books, and I'll see you all on Monday.